So a differential equation might look like, there's my derivative part that's saying how my population of sea turtles is changing with respect to time. Now, if I add in a 1 over n, this becomes the per capita growth rate. And that per capita phrase, that means per individual. So if my growth rate were 50%, and then I had 100 sea turtles in the population, then that per capita growth rate would be the 50% times 1 over 100. So it's a measure of relative to the size of the population, how big is that growth rate, that per capita growth rate. So we're introduced to a bunch of different models over the course of this textbook, really, but specifically in chapter 7. I'm not a biologist, I'm just making stuff up. So let's say that our population of sea turtles, that the per capita growth rate is, I don't know, let's go with 0.3 times 1 minus n over 200. So what this is saying, like if we look at this in pieces, so as n gets really, so when n is really small, this piece is going to this differential equation says that the growth rate for the population depends on or is a function of how large the population is at any given time. Meaning dn dt is kind of like our function. This is our f. And it's a function of the population n. 0.3 times 1 minus n over 200 times n. Now I said that we were introduced to the logistic growth equation back in 17a when we were talking about recursively defined growth. And one of the things that we talked about in that context was, and there are a couple of different phrases for it, but we might have been talking about equilibrium values or fixed points. Well, what that means in the context of our differential equation, if I'm at a fixed point, or in equilibrium, that means that my rate of growth is 0, that population isn't changing. So our dn dt would be equal to 0. So for this equation, we have a couple of those fixed points or equilibria. One would be if n is 0. Now biologically, this is almost always a natural answer, because if you think about it, if I have no sea turtles, then there can be no sea turtles in the future. So if my population goes to 0, then there can't be a change in the population. Our other fixed point here is going to come from setting this equal to 0. And if 1 minus n over 200 is equal to 0, then that would lead us to n equals 200. So this fixed point or this equilibrium, we sometimes refer to as the carrying capacity for the logistic growth model. Because when I reach a population of 200, that tells me that dn dt is 0. And dn dt represents how that population is changing. So when I hit 200, this population will no longer be changing. It'll be fixed at 200. So the question is, we know that if we start with no turtles, we get no baby turtles. And if we start with 200 turtles, there will always be 200 turtles according to this model. But what if we start with other populations of turtles? other numbers in our population. There are a couple of different ways to think about it, and I'm going to choose to approach this graphically to start with. I just wanted to remember this is my d and dt. Okay. So here's my n. So this axis is going to represent the population or the number of sea turtles that we have. And since I don't know what negative numbers of sea turtles would be, like zombie turtles or something, we're not going to deal with that negative realm. We're really just going to be living over here. Now this axis, this is going to be my function, which is dn dt. So before I even get started sketching a graph of this, I want to talk about what these different parts of the graph actually mean functionally. In this case, my vertical axis or my y-axis is telling me about how the population is changing. So every point that's above my y-axis in this graph means that dn dt has positive values. Well, if dn dt has positive values, thinking back to 17a, if my derivative is positive, then that tells me that function is increasing. So n is getting larger. Similarly, if I think about what values down here below that axis look like, well, down here, because that vertical axis is a measure of dn dt, down here, our dn dt is negative. And that tells me if my slope of n is negative or if my change in n is negative, then my n values are getting smaller. Now comes the fun part. So I want to sketch this curve, and I don't know exactly what it looks like, but we can get started because we know that n equals 0 and n equals 200 are both places where the n dt would be 0, or I should be here. So 0 and 200. Now in between, if I look at this and I think about distributing that n out, well, if I distribute the n through and I distribute that 0.3 through, I think this is going to look like 0.3n minus 0.3n squared over 200. Which means I'm looking at a parabola that's concave down because my n squared term is negative. So filling in this graph, it's going to do something like this. Now comes the fun part. Oh wait, I said that was the fun part. Here's the next fun part. So we know what happens if we start with 0 turtles. They're all dead. It's sad. We know what happens if we start with 200 turtles. Our population lives with 200 turtles forever. Well, let's think about what happens when we start with 50 turtles. So if I start with 50 turtles initially, then this graph represents how that turtle population is changing. So it's telling me how to change the population. So if I start with 50 and then I come up to the graph, then at 50 turtles, this graph has a value that's up here, which means the NDT is greater than 0, which means the N would get bigger. So I'd start with 50 turtles, and that population would grow a little bit. Well, now I maybe have 55 turtles, and then this curve tells me what's going to happen to the population. So at 55 turtles, I'd come up here and go, oh, I'm still above the axis, which means the NDT is greater than 0, which means my N gets larger, and my larger N values are this way. So everywhere in here, my N values continue to grow. Well, those N values are going to grow until they hit 200, because we already know that when my population hits 200, our growth stops and doesn't change anymore. Now let's think about what happens if our population started above 200. So let's say that instead of starting with 50 turtles, we actually started with 250 turtles. Well, now, if I start at 250 turtles, this curve is telling me how that turtle population changes. So I'm going to take that 250, come down here to the curve, and say, oh, because I'm below the axis, I know that dNdt is less than 0, which means my N is getting smaller. So I had 250 turtles, but now that's actually going to decrease, and I'll be somewhere in here. Everywhere on this portion of the curve, because those dNdt values lie below the axis, I know dNdt is negative, and N will get smaller. My guess is that you all could come up with biological reasons why this piece might be true. Maybe there's competition for resources. Maybe there's actually only enough food or habitat to support 200 turtles. So if that population gets bigger than 200, it's going to naturally die back down to 200. We call this a stable equilibrium because a small perturbation, that's our mathy term for saying if something were to happen in the environment that shook us from 200 one year, maybe there were storms during egg laying season and more of the turtle eggs didn't hatch that year. So we were kind of at this stable population of 200, but something in the environment happened in a single year that pushed us down below 200. Well, this model says it's going to climb, our population is going to climb back to 200. By the same token, maybe there was a strong, I am not a biologist, maybe there was a strong upwelling and there was an abundance of food for sea turtles one year, and so more of the baby sea turtles survived. So all of a sudden there's this spike in population. But that was an abnormal condition, and so when things return back to normal, this population is naturally going to creep down, back down to 200. So we call this a stable equilibrium. Now it turns out in this case that 0 is not a stable equilibrium. Although we don't really want to think about those zombie turtles in the negative N territory, we can still graphically look at what the model is saying. And the model is telling us that if we were to start with N values over here, then to look at how it would change, I'd come down to the curve. Well, because I'm below the axis, I know our N values would get smaller, and that means that we're pushing this direction on the graph. So this 0 point, we know that if we start with 0 turtles, we have 0 turtles, but if we move just a little bit away from 0, this population is going to grow up to 200. So we call this an unstable equilibrium because all of the values are trending away from it if I move off just a little bit. Now we can take this graphical analysis actually one step further. So this is kind of a weird graph because here we were graphing our population of turtles, or sorry, we're graphing our change in population of turtles as a function of the number of turtles in our population. But maybe what we actually want to explore, I'm going to keep this up here. So we're going to do something with it in a second. But maybe what I actually want to explore is what that population looks like as a function of time. Well, and since we're not going to have a negative population, let me change my graph. No zombie turtles. So there are two population values where it's easy for us to sketch what's happening over time. And that's our two equilibria. Because if I start with 0 turtles, then I stay at 0 turtles forever. If we started with 200 turtles, then we stay at 200 turtles forever. But now let's think about what happens if we started at 50 turtles. Oh, I wrote 20. I meant 200. Thanks for catching that. So what would it look like in terms of this population over time if we started at 50 turtles? Now here, I'm really drawing on those 17A skills, and I know I'm kind of stretching us a bit, but that's okay. So I want to come back here, and let's see, that's 100, so there's 50. This graph is essentially a graph of my first derivative. It's a graph of dn dt. At this point on my graph, I know that the tangent line to this curve would be flat. Well, the tangent line to the first derivative means we're talking about the second derivative. When our second derivative is equal to 0, thinking back to 17a, a second derivative being equal to 0 means that we're looking at an inflection point. So when I come down here to be looking at this graph, what actually happens is we start off with a population of 50 and we're growing, but we hit that value that corresponds to the inflection point, and this population we're going to get an inflection here. So if this is concave up, then we get an inflection to be concave down. And this is sort of that classic shape for a logistic growth curve, where we start off with slow growth, and then there's a period of very rapid growth, and then we slowly, exponentially approach that carrying capacity of n. Now, if we look at the model where we started at 250, because this curve is just a parabola that keeps going forever, as we move from 250 towards 200, we do not pass through an inflection point, which means the concavity doesn't change. So if I'm up here at 250 and I have to get down to 200, then what that curve would look like, the shape of that graph, we can't have an inflection. We have to stay with the same concavity. This is going to kind of look like this. Likewise, if I started out at a value right in here, like maybe I started off with 175, because I'm already on this side of the inflection point, between 175 and 250, as we move through there, we're not going to hit another inflection point on the curve, so our concavity is not going to change. And if I start up here, I'm just going to see that more exponential shape heading towards that carrying capacity of 200.